In the book, AI, L4IR Leadership and the Fourth Industrial Revolution, there is a chapter on quantum computing, and one area discussed is the cybersecurity transition from the quantum hack vulnerable state to the quantum hack resistant state that requires moving from number theory to geometric algebra. And the acronym RSA stands for Rivest-Shamir-Adleman, named after its inventors, Ron Rivest, Adi Shamir, and Leonard Adleman, and refers to the widely used public key encryption algorithm.
So imagine the greatest heist of all time. But the target isn't some bank vault full of gold. It's everything. Your emails, your bank account, government secrets, all of it. And the bad guys have a brand new tool that can pick any lock in the world. The race is on to invent a whole new kind of lock before they get in.
So that's the big question, right? How do you stop a thief who can break any lock you've ever built? Well, the answer isn't just a stronger lock. It's something else entirely, something that's going to bend your brain a little bit.
To really get what's coming, first we've got to understand the lock we're all using right now, every single day, probably without even thinking about it. This is the bedrock of pretty much all of our digital security. It's called RSA encryption, and for decades, it's been the absolute gold standard. The best way to think about it is like a special padlock. Anyone can find it and snap it shut, but only the person with the one-of-a-kind key can ever open it back up.
So how's this magical lock made? Well, it all starts with a secret recipe. You take two secret prime numbers, we can just call them P and Q. Then you multiply them together to get a new, absolutely gigantic number. Let's call it N. That number N is the public lock that everyone can see. But the only key that can open it is knowing those two original secret ingredients, P and Q.
And here's the kicker. For any normal computer, taking that huge public number N and trying to work backward to find P and Q is, well, it's basically impossible. We're talking billions of years of just guessing. It's like trying to unbake a cake to figure out exactly which farm the eggs came from. That insane difficulty is what our entire digital security has been built on. But, as you've probably guessed, there's a new kind of computer coming. The quantum computer. And this thing, it just doesn't play by the same rules. It has a master key. Now, the real threat isn't just the machine itself. It's a very specific program, a recipe that it can run. It's called Shor's algorithm, and it is the ultimate lockpick for our old RSA system. And here's where it gets so incredibly clever. Shor's algorithm doesn't waste time trying to guess the secret numbers. No, that's the slow way. Instead, it kind of listens. It listens for a hidden, repeating rhythm that's buried deep in the math of the lock itself. Let me put it this way. A classical computer is like a burglar trying every single key on a massive keyring one by one. It's just brute force. But a quantum computer running Shor's algorithm, that's like an expert safecracker pressing their ear to the vault, listening for the faint clicks of the tumblers, and using that hidden rhythm to just pop the door right open.
So, yeah, our old lock is fundamentally broken. We can't just build a bigger version of it. We need a completely new design, from the ground up. This means we have to completely change how we think about hiding a secret. The old security was all about what we call number theory, hiding a secret in a giant, hard-to-factor number. The new security, though, is based on something completely different, geometric algebra. We're not hiding secrets in numbers anymore. We're hiding them on a complex, sprawling map. And when I say complex, I really mean it. You know, we live in 3 dimensions: length, width, height. This new security system operates in a mathematical space that has over 1,000 dimensions. Yeah, try to picture that in your head. You can't. Nobody can.
The fancy name for this new method is lattice-based cryptography, and it's all built around solving a problem that is ridiculously hard. It's called the shortest vector problem, which basically just means trying to find the closest point to you on this massive 1,000-dimensional grid.
So how do you use this to hide a secret? It's pretty cool. First, you pick a secret spot on this giant grid. Then you use a public map to figure out where you're going. But, and here's the brilliant part, you deliberately add a tiny random bit of noise, a little error. This shoves your final location just a little bit off the perfect grid lines, creating a public key that's intentionally fuzzy.
Now, you might be thinking, hold on, why would you add an error? Isn't math supposed to be perfect? And that's a great question. But in this case, that little bit of intentional messiness, that noise, is the secret ingredient. It's the very thing that makes this new lock unbreakable. And this really is the key to our whole story. How on earth does a tiny bit of random chaos manage to defeat one of the most powerful computing tools humanity has ever dreamed up?
Well, to break this code, a computer would have to look at your fuzzy public key and figure out which point on the original grid is the closest one to it. Now, if this were a 2D map, that's easy. You could just look at it and see. But in 1,000 dimensions, the very idea of closest becomes a complete geometric nightmare. There's no up or down, and that noise makes finding any kind of clean path impossible.
Now let's go back for a second. Remember Shor's algorithm? What was its special trick? It needed a clean, repeating pattern, a mathematical rhythm, a predictable cycle that it could find and lock onto.
Well, that little bit of noise we added on purpose, it's a saboteur. It's designed to do one thing: smash that pattern to pieces. It destroys the rhythm and replaces it with pure mathematical chaos. It erases the very thing the quantum computer was built to look for.
And this is the beautiful punchline. Because the pattern is gone, the quantum computer loses its superpower. This fuzzy, noisy, chaotic math looks just as confusing and impossible to a quantum computer as it does to the laptop I'm using right now. The quantum advantage, it just vanishes.
So in the end, we're fighting the hyper-ordered mind of a quantum computer with a little bit of engineered chaos. Our new digital world is literally being built on a foundation of perfectly imperfect math. And it makes you wonder, doesn't it? If a little bit of targeted noise can secure all our data, what else can we protect by embracing a little chaos?
Kent Kaufman, the author of the book AI, L4IR, Leadership and the Fourth Industrial Revolution, has over 30 years of experience in executive roles, management consulting, and executive coaching. He has coached and mentored many Silicon Valley CEOs and top management teams. His book is available through Amazon, Barnes & Noble, and Ingram Spark, and his audiobook is on Spotify.